Hello, my name is Varga and I want to present our paper Wavelength-aware 2D convolutions for hyperspectral imaging. In this work, we focus on hyperspectral imaging and propose a 2D convolution which is based on wavelengths instead of the input channels. Let's look on the motivation behind this approach. We introduce a suitable model bias, namely similar wavelengths show similar features, which allows us to reduce the number of trainable parameters significantly. Further, the model is interpretable, so it allows you to inspect the learned camera filters and maybe use them further. On the right side, you can see an overview of the approach. As an input, we have the hyperspectral cube and the wavelengths of each input channel. And the model itself has two trainable components, the camera filters and the kernel prototypes. By using the input wavelengths, we can sample the camera filters and the kernel prototypes for this hyperspectral cube and can create the 2D convolution kernel for this specific input. Let's look on an example. Here at the top we can see a hyperspectral cube. The difference to normal RGB images is the larger number of channels. Here at the bottom we can see a normal 2D convolution, which is here used for the classification of ripening evocators. We can see that one range which is, for example, important for this classification task is the range between 700 and 800 nanometers. We will see here in this range similar features for the channels. The problem now is that for a 2D convolution we have to learn for each input channel a similar kernel. Means we have a lot of redundancy here in this range. For our approach, we want to learn only one kernel in this range and the distribution of this kernel. So we can see here that we use Gaussian distributions to learn where we can find specific features. As a result, we have a wavelength-aware 2D convolution, which allows us also to build camera-agnostic models. Further, the whole model is end-to-end trainable. That means the camera filters and the kernel prototypes can be learned in a data-driven manner. Further, the learned camera filters could be also used to build multispectral cameras for a specific task. Here on the right side, you will now see the training procedure. Here the training loss and the validation loss. And on the right side, you can see how the model finds the correct spots or the important wavelengths for this classification task. After the training of the model, we can use the found camera filters to build a simpler system or use them in other tasks. Thank you for your attention. You will find our code at GitHub, and I hope I will see you later in the poster session. Otherwise, I wish you a nice further conference.